as far as math and physics?
I took physical science freshman year, which was kind of physics.
So what all does that include? You got like physics and chemistry.
Yeah, a little bit of chemistry. I think calculating energy.
Okay. And math wise,
I took geometry last year, and I'm taking algebra 2 this year.
good. Geometry is going to be very. And
I'm taking calculus right now.
Okay.
And taking physics right now. I'm also taking physical science.
perfect. Dustin, how would you feel about moving over to the whiteboard?
Oh, yeah.
I think that might be easier. Make sure we're all.
They want their little packets, or take your packet.
Thank you.
I don't know if you need it or not. Ethan, Kira's got the full book of this on a PDF. You'll put it on some Google something or.
Alright, change the
Oh, you're all right. You just leave
change
it
the
off.
channel so long. Okay. So you're in physics right now. You did some physics.
Yeah.
If you guys want to bring chairs over if you want. Okay.
Ethan's from the School of Hard Knocks. That's what
Free
Ethan's
body
in.
diagrams. Does that mean anything to either of you?
I heard some of it, but I don't.
Okay.
I've heard of it.
So we'll just start off pretty basic. We aren't going to go in depth. You don't need to take notes or anything, but just some basic principles. Okay, so let's say we have a block there. Free body diagram says all the forces that are acting on it. Now, like simple one, gravity. Okay, so you have a block sitting on a table. There's a gravitational force on this that pulls down the center. Now, if you have, let's say you have a block and you push it with a force, what happens? If you have something, I have this sitting here and I push it, what happens? It moves. Yeah, there we go. So the only way that you get stuff to not move is when all the forces that are acting on it are balanced out. So if you have one force pushing one way, one force pushing another, I push this way, it moves that way. I push this way and this way, it doesn't move. Same thing, so like if you have a gravitational force acting on something, and then it's sitting on a table, the table applies a force in the opposite direction, and your block sits still. Okay, so there's basic balance of forces, and now that's true in all directions. And so like let's say we had block sitting here and sitting on table, you know, someone pushing this way, and then, or here, we'll do okay, block again, yeah. Let's say you push on it in this direction, and you push on it in this direction, and this direction. What would happen there? Okay, so like let's
Ethan's like, would it grow an ear of corn?
we will what else is this?
Was that mean or funny, Ethan?
Yeah, all sorts of random junk around here. Okay, Ethan, come over here.
Okay.
So if I push like this, it moves that way, right?
Mm-hmm.
So there's the bottom of this box pushing up. Put your finger there. Now I'm going to push down. What happens? It doesn't go anywhere. Why? Because whenever you have a force acting, and this is where you took geometry last year, you've taken geometry. Remember triangles? They spent like this whole entire year on triangles. Okay, so different situation. Instead of having this, let's say you had a force here and a force here. That's easy to answer, right? What happens to the block now? It doesn't move. So what you can do, and this is what we're going to be doing for all the analysis we're doing, is you say this force here we're going to pretend that it's actually this force here and this force here. So you ignore this one, and you have those two forces. Now, does that look familiar to you guys? You have a force, and a force, and a force, and you have a 90-degree angle. We got a triangle. We can work with that. Okay, so what we're going to be doing is pretty much breaking these down into components. So going back to our right triangle, we'll do a little bit of number crunching here. Let's say we have a 30, 60, 90-degree triangle. Standard one, all add up to 180, we're good to go. If I tell you that this side is 1 inch, can either of you figure out what the other sides are? Let me grab a calculator for you. Unless you have sine tables memorized.
Kira's got it worked out in her head, don't you?
I need to.
Here.
Can I just draw 30
Yeah.
seconds? Is it? There's like x2, x, and then it was.
I think that's a,
There was.
isn't it 3, 4, 5? Okay, do you remember sines and cosines?
Yes.
Okay, I would just use that for this.
Okay.
So you remember your law of sines, or like, okay, so sine of your angle is equal to what?
Sine is opposite over hypotenuse.
Yep.
So.
Do you want to just write that over there?
Yeah.
Sine equals, if you need a different marker. Do you, is this looking familiar to you?
Kind of.
Okay.
I didn't have the best teacher.
So, sine, and then what's cosine?
Adjacent over hypotenuse.
Yep.
Do you want tangent?
Yep. Okay, so how would we figure out this side?
You take the inverse tangent. No, you take the tangent of 60. So just the tangent of 60.
Which calculator there?
The square root of 3.
Okay. And that's some random decimal. Okay, and then what would you do to find the hypotenuse?
You could take the cosine of 60.
Yeah, there are a bunch of different ways to solve this, so.
One half.
Well,
And then
cosine of 1 divided by the cosine of 60?
Oh, 2.
There. Okay, so we would know this is square root of 3. And this is 2. Okay? So we can do that with forces as well. So back to our block. We'll leave that.
Kira's like, really? I just wrote all that out.
it's okay.
Okay, so we have our block here, and you know we'll give it a nice little surface so we can act on that. So if this is at a 45-degree angle, then if we want to break this in, let's say it's 500 pounds. Pound force, don't worry about it. Okay, so that's a nice easy one. You got 45, 45, right? Because 90, 90, 180. And you have your hypotenuse is 500. And do that, then we want to take, let's say, our sine. So sine of 45 is equal to opposite, which we don't know, which we're trying to figure out, over the hypotenuse, which is 500. Okay, multiply by 500. So sine 45 times 500. Can you pull it? Figure that out?
353.5533906.
Give me the
353.
Round it up. 353. 353. Okay. Now the nice thing is 45-degree angle, so we know this and this. So we can say 353. Ignore this 500-pound force. This box has 353 and 353. So if this box is not moving, what do we know about the other forces acting on it?
They're equal.
Yep. So
Boom.
if we have a force here,
Good man.
what's that going to be? Yep. And same thing over here.
353.
Okay. So that's basic. That's for a single point that we are representing with a block. Now let's get a little bit more complicated. Instead of having a block, we're going to have a truss, a very simple truss. So we're going to build it out of 3 elements here. Now, truss construction, everything is a pin connection. So if you think about it, you have, let's say you have 2 pieces of wood that were bolted together. And they're bolted loosely. Another one here. Now, if they're loosely bolted and you push down here and you hold this one, what's going to happen? It's just going to go down like this and it's going to end up like this.
It's gonna like turn.
Yeah, it's going to rotate. There you go. So it's going to make a circle. It's going to spin like that around this point here. Now, the reason that we use bolted connections like this is because it prevents a moment load from being applied. Which a moment load was if, let's say instead you welded this all the way around and you held this down and you push down here, what happens? If you hold this really tightly and you push down there and you have a welded connection.
All the force goes to the welds.
Yeah, you have like this force path. If you hold that there and you push down there, like we got a bunch of welded pieces over there and you can jump on it all day long and nothing moves because even though this piece wants to move this way, it can't because there's a weld preventing it. And essentially, as soon as we start doing that, the math gets a lot more complicated. So we're gonna go easy route and do bolted connections for this because then you don't have to worry about moments. All you're worrying about is X and Y forces. Okay. Tension and compression members, like these, force can only act in one direction. So again, if you give me a second here.
Any thoughts, Kira?
Is this making sense a little
Yes,
bit?
it
Okay.
is.
Okay, good.
How's them soybeans, Ethan?
Good.
All right.
Oh, okay, here we go. Use a little piece here. Okay. Actually I need a piece with a hole through it. Yeah, a piece of cardboard. That'll be perfect. Do you have any
I don't know what he's doing. You guys get pushing around the block?
These are some professional grade teaching aids. Okay, so hold it by the pen. Okay. Now, can you do anything if I push like that? Or like this? No. Now, if I push like this, you can push against it, right? And if I pull like this, you can do something. But if I decide to pull this way, it's going to flip around so that it pulls in line with the force. So the only way that a piece like this with a pin connection on the end can apply a force is in the direction that it's in. Now you have two different options. You have tension and you have compression. So tension is when something's being pulled, like a string. So this is tension. Things fail in tension by tearing, or if it's more of an elastic material, you'll have what's called necking, and you'll get like some deflection here, or it'll start getting skinnier. Think about like a rubber band. You stretch it, it gets thin in the middle. Compression is different. So if I push on this really hard, what's going to happen? So there you go. This is called buckling. So what happens is if you have, and like let's say we just have a stick sitting on the ground, and you push down really hard here. Okay, so big difference here. If you do that, it's going to bend. So it's going to go like this, and then as you push down further, it goes like this, and it just bends out of the way. If you have a really, really short stick, and you do that, is it going to do the same thing? So I think you're right. You have the right instinct that like it's not going to function just the same way. I have a good example here. Okay. So just a little piece of plastic. Where did I put those two? Oh, here we go. So I've got two of them, right? Put one here, this just to spread the load. I can stand on it. See, the block of wood is still off the floor, and they're perfectly fine. Now, which one of you two brave souls wants to try that up here? Neither of you, because you know it's just going to bend like that.
Don't be a little girl. No offense.
You know that those pieces are just going to fold out. Whereas you saw with the little short ones, you're like, oh yeah, that's going to be fine because it's sitting on the floor. And so same thing happens here. So what really happens if you have a really small piece, let's say you have a little block like this, if you put enough force on it, what's going to happen is the sides will start bulging out, but instead of like bending to the side, it'll just kind of squish it down like a pancake. But we aren't going to be dealing with that because as soon as you have a long skinny member, it buckles. And there's like equations for figuring out when stuff buckles, when it doesn't, and how it buckles. More important thing, because you don't need to get into that, that'll be if you go into engineering and you take entry
When
level
you go into
engineering
engineering.
courses. Where did I put my paper? Give me a second here. There.
What's it take to buckle a piccolo?
I don't want to find out.
Oh,
That was a very expensive experiment to perform. Well, okay, I guess let's go back to the trusses for a little bit. Okay, so one nice thing we have free body diagram. Okay, let's say I put 500 pounds here. Now, we're gonna have a pinned connection here, and a roller connection here. Don't worry about it. Okay, these two can act in both directions. This one, or I guess this one can act in these directions, that one can only act in one direction. Now, how do you think that load is going to get spread? If you had to draw or like figure out what forces are going to keep this thing from moving, what would your guesses be? So you got 500 pounds pushing down. Okay, so go back, pretend like this is your box. Okay, so you got 500 pounds pushing down. What would you have to have pushing up to keep this thing from moving?
500 pounds.
Yeah, 500 pounds. Now,
Good man.
what you'd like to do is say 500 pounds here, right? That'd be nice, that'd be easy. We don't have anything here to apply 500 pounds of upward force. So clearly that's not how it's gonna work. The only two places we can apply force are the corners. Now, we could just say 500 here, right? Does that work? No, because as soon as you have, so let's say I'm pushing, need something that doesn't roll. If I push here and here, it spins. Now, if you push here and here, it doesn't spin. And the nice thing is, because this is symmetrical, and we won't get in, there's a bunch, like some fairly straightforward math to say how the forces are distributed, just so long as you keep this symmetrical, the forces are symmetrical. So, that's not 500. What is this?
250.
There we go. And 250. Okay. So now we're starting to get some information here. So we know we have 250 pounds going up this way and 250 pounds going up this way. And let's see, my example I added 60, 60, 60. This is very poorly drawn. Let's say this is 60 degrees, this is 60 degrees, and what's that last one?
60.
Yeah, there we go. Getting back in geometry. Okay, now, what I was saying before, this can only act in this direction. Any force that applies has to be acting in this direction. So let's do a free body diagram for that point. So we know we have 250 acting up. This is a pinned connection, so we can have a force acting this way. Question mark. We have a linkage here that can be acting in this direction. We're gonna start labeling these. Okay, we're gonna say this is point A, this is point B, this is point C, this is linkage 1, linkage 2, and linkage 3. Okay, so we know that this linkage 1 can be acting in this direction. And we know that this linkage 2 could be acting in this direction. Okay. So we know that this thing isn't moving up and down, right? We know that's pushing up with 200, so what do we know about what's going to be pushing down? Yep. So we need a force here. For this to be in equilibrium, we need a force here that's acting 250 pounds. What do we have that could exert a vertical force on it? Can this linkage do that? No, because it's going in this direction. Could the other pin connection, or like the other portion of this? No. So the only thing that we have is this. So we know that the y component of this force that this is exerting is what? Yep, 250, and it's going to be pointing down. Okay. So we have 60 degrees, we have 250, we have, and we have an angle, right? So we have a triangle here that we can start drawing out. Being left-handed is annoying. Okay, so we got 60 degrees. And we know that this is 250 pounds. Okay? So, can either of you tell me what that's going to be? What the x component of the force from linkage 1 is going to be? Ethan? Here's a marker.
No.
Do some math. Okay, remember
It's
your
over here.
sines, cosines, and tangents. So we have an angle here, right?
Yeah.
And we have an adjacent length, right? One of the side lengths. Okay. So what would we use if we have an angle and an adjacent and we're looking for the opposite? So we have angle, right?
Yeah.
And we have the adjacent and we need the opposite. Which of these has adjacent and opposite?
Oh,
And an angle?
Tangent?
Yep, tangent. Perfect. Okay, so why don't you go ahead and write that out here. Tangent of 60. Is equal to your opposite, which we don't know, right? Divided by your adjacent, which we do know. So go ahead and write that in 250. Okay, so now we can solve that for your opposite, right? What would that be?
So you had divided by 250. So what do you got to do to the 250? Now you're just in the basic algebra. You're thinking about tangent too much.
Multiply?
Yep.
Yeah.
Okay.
Boom.
This tangent 60, that's just a number. Ignore it. It's just a number. Once you figure out the right thing, it's just a number. So 250 times your tangent 60.
433.
Okay. Go ahead and write that out. And what is that equal? That's what you're...
Nope, do it on the right side, just to keep it clean. There you go. That's your opposite, right?
Yep.
Boom.
There.
Nailed it.
So that right here, I'll take the marker back. So we know that this is 433. We got a right angle here. Okay, so we know that the x component of this is 433. Okay, now can we say what the hypotenuse is? There are a couple of ways of going about this. I like a squared plus b squared is equal to c squared, so go ahead and take that squared plus that squared and square root of that.
And we're not worried about his couple of ways. It's a squared plus b squared equals c squared.
Can you also do like trig ratios?
Yeah,
What?
You could. You definitely could.
Could you do what?
Trig ratios.
She's got it. She's got it.
If you're a loser.
If you wanted to, you could do your sine. You could do your cosine. It's whatever. Or you can do a squared plus b squared equals c squared. It's all the same. Trig works out like that. It's nice.
499.9.
499.9. We're gonna say 500. Wait. Okay. So we know that this is acting at 500 pounds of force going down this way. Goes back up that way. Okay. Now, nice thing is, this is symmetric. So, any guesses as to what this one's doing? Yeah, there you go. Okay. And we know from that if there is 433 acting this way, we need another 433 acting that way, right? So this one is 433. So there we go. We've solved all the forces in this.
So is it 433 altogether? Like each side is acting on each other, or do you have to split it in half?
No, it'd be 433 because
The force goes on both pins.
yeah, pretty much. And so this is getting to kind of basic structural. So now which way is this? And just intuitively think about it. If I push down, what's going to happen to this? Is it going to get pushed in or pulled out? Pulled out. Yep. And you can tell that by saying, okay, which direction, if this is pushing this way, which way are our X and Y forces pushing? Is it going to be pushing up and over this way? No, it's going to be pushing in line with this. So it's going to be pushing down and over to the left. So those are our resultant forces, and these are the forces that are in each of the members. Now, I'll give you a very brief rundown on structural members. I think we already talked about tension and compression. Generally, when you have like a beam, we'll do a simply supported one. Or we'll do a... simply supported, whatever. Okay. So if you have a beam like this and you put a load in the center, what happens is this stuff here all wants to get crunched together. And all the stuff on the bottom is going to get pulled apart. If that does that kind of make sense to you? Like if you think about it intuitively, man, I really wish
Go back to that piece of plastic.
I mean, you need
Hold that. Now you bend it. So see, obviously what's on the top is coming in, and kind of hard to picture because it's so thin, but what's on the bottom has to go back out.
This actually might be a better example. This is actually great. So watch the gaps there. And Dustin, you want to push down the middle of that?
Oh.
Or I can do it. Okay, so watch what happens to them.